many project proposal reviews and system design reviews, and quite often, as I see people talking through the design, and there's this, oh, for this particular feature, we're going to use machine learning. And then I ask how, and the answer I get is, well, that's what the ML will figure out, right? So I'm hoping by end of this session, you will have a greater understanding of the how part. So not only use ML, but actually how to use it and how it works. So with that, let me jump right into it. So yeah, let's just to set the stage, AI machine learning landscape, right? So artificial intelligence, that is the overarching concept here, and AI basically strives to achieve human-like intelligence. And AI uses a bunch of technologies, which include machine learning as part of it, but also natural language processing, statistical techniques, many other conventional programming techniques, and so on and so forth. Machine learning is a subdomain within AI that is about algorithms that learn how to automate one or more tasks. And that can be broken out into three types: supervised learning, which we will go more in detail today. There's also unsupervised learning, where we just provide the data and the algorithm tries to find patterns. So it is akin to what is called clustering. So it will find clusters of data that are related for us to get insights from. Reinforcement learning is also another interesting concept, where the idea is the algorithm basically comes up with a sequence of actions or sequence of decisions to maximize a reward. That's a whole big. These are whole big topics in itself. Probably worthy of a separate tech talks. Natural language processing deals with the study of algorithms that can interact with humans via natural languages. So English, Japanese, Korean, Chinese, etc. And neural networks is a special class of machine learning algorithms. And within that, deep learning is a special class of neural networks. Over the last 20 years, there's huge amount of research and just amazing growth in these areas. And then we're starting to see deep learning and neural networks used across the board. So there's so much overlap being used for all kinds of things as we go into, as we'll see later on in this session. So yeah, as you can see, there's a lot of overlap within these subdomains in artificial intelligence. So yeah, artificial intelligence uses a number of these techniques, and these are like some specialized techniques within that domain. So let's talk about programming versus machine learning. What is the difference? And there are some key insights here. So I'm gonna talk about the traditional programming, and I assume like most of you are familiar with programming since we all work at Microsoft. So this here you look at is a simple function here, which converts Celsius into Fahrenheit, Celsius temperature scale into Fahrenheit. So in traditional programming, we basically write code to code this function as a couple of lines of code in any programming language. So this function is basically described in this algebraic form here, which is a linear function, right? Linear algebra. So that is typically what we approach in programming. Right? Machine learning is we flip it, right? So we start with, instead of the function and code it here, we start with the data, right? So we have this table of data, Fahrenheit, Celsius, right? Or Celsius to Fahrenheit. Then we try to apply a supervised learning algorithm to learn this function, right? And by that, what we mean is we're trying to figure out the value of W and B that completes this model of our function and then helps us basically convert any Celsius value into Fahrenheit, right? And that's essentially the model. And just a call out here, supervised learning is responsible for most of the significant breakthroughs in AI, including machine translation, face recognition, image classification, fraud detection, spam detection, speech recognition, and so forth, right? So there are some interesting things to note here, some key observations. First of all, we talk about modeling, right? So modeling is just not new to machine learning. In fact, modeling is everything in computer science is a model. We model the real world and then solve problems for the real world. So if you look at traditional functional programming, we are modeling the variables, right? And the output, and then solving through various functions and equations. For object-oriented programming, again, we model real-world objects into a program, right? And then build software around it. The same thing we do in machine learning, right? We are modeling the data and to learn the function, we're just inverting it. The second observation here is why this is so interesting, because we have lots and lots of data, right? And so we know some functions, but we don't know all those functions, right? So this machine learning is very powerful because we have lots and lots of data, and we know that there is correlation, causality, and those things exist. And also there is some of the things that we would love to predict, right? We would love to also figure out the underlying function, right? And this provides us a way to learn it. So that's what makes machine learning super powerful. And with all of our connected internet and just more and more information age we're living in, there's just we are producing every day more data than we have done historically. So that's why the relevance of machine learning in future as we go. This is, so think about, we talked about this model, right? Celsius to Fahrenheit. So how does it look if we want to visualize it? So this is a simple linear relationship, right? That can be.
There's a 63 role available in Chris Healy's organization right now, but like I need to wait to see how this promotion thing goes.
Please mute if you are not speaking. So one question is, how does this learning algorithm work, right? So the learning algorithm basically works, it starts with some values of W. It needs to find out this W and B that makes up this function, right? So it will keep trying various values of W and B until it reduces the error, right? So this is the actual data, and then it will predict some value. And with each example, it will try to reduce that error. And that's why it's called supervised learning, because we are training the algorithm by providing real examples, right? And then helping it to reduce the error between predicted value and actual value, right? So when we visualize it, it looks like a line, and then the learning algorithm can start with a line that looks like this, but as it sees more examples, it will converge to this line with 100% accuracy. Now, this is a very simple model, which is just talking about two variables, dependent and one independent variable. Now, if we were to, let's say, predict house sale price based on square footage and condition, only these two factors, right? Then instead of a line, it would look like a plane, right? The linear algorithm is trying to fit this plane to as many data points as possible, right? Now this starts to get more complex, right? Because as you can see, there's a drift. Now you can't really find, the algorithm can't find one plane that fits all these data points. The relationship itself may be nonlinear. We'll get into that. And then predicting the value of, let's say, house sale price it may depend on many other factors. Maybe there's like 100 factors that it depends on. So yeah, for example, like Zillow lost over $500 million predicting house sale prices, and then they thought they could buy at value and then sell it. So yeah, I mean, can be basically do not try this at home. That would be my recommendation. So two types of supervised learning. We talk about supervised learning, right? We're giving examples to the algorithm, and it's trying to figure out the underlying function, right? And by adjusting the weights to, and then, but we looked at a continuous value example, right? Where we're predicting the house price. The other, which is called regression. The other type is called classification, where instead of predicting a value, we are predicting a class or a label, right? So let's say, for example, house interior design, right? But the idea behind how the ML algorithm works is the idea is still the same. It's trying to fit a curve, right? So in this example, it's trying to fit a line, but more generally a curve in a multidimensional hypervector space, right? So in regression, it's trying to fit all the data points, as many data points as possible. In classification problem, it's trying to fit a curve that separates the classes the best, right? So in this case, red dots versus green dots. But the idea is still the same. Find the curve that best either fits the data or separates the data. Okay, so this is model performance and generalization. This is a very important concept here. So I want to just spend a couple of minutes here. So let us say the ML task is to classify blue dots and these red dots, right, or yellow dots. And this is our training data. So when we use some learning algorithm and it finds these curves that separates these data points out, right? Now this looks pretty good for this training data, right? It's separating out these red versus blue dots pretty well. But when we roll it out and we use it on new data in real world new data, it seems to be not doing so well, right? So there's a lot of these blue dots in this region, orange or yellow region, and vice versa. So that is an example of an overfitting model. What overfitting means is that we train the model so it's like overfitted on the training data. It's too specific to the training data. And hence it's not generalizing well when on new data, right, on the real world data. And so that's the fundamental tension in machine learning, how we can come up with the simplest possible model, right, that works well, that we train on the training data, and that generalizes well, yet it also performs well. Okay, so that is the fundamental tension in machine learning. The other thing to note here is, well, what do we do if the actual data distribution looks like this, right? If we have blue dots and orange dots all over the place, how do we solve this problem? So there are many different techniques, but what could be happening here is that maybe we need another factor to build this model, right? Because what we are trying to do, separate these data out, it depends on more factors than what we have taken into consideration. We definitely we can't find a linear solution, meaning like a line or a plane that separates them. So it's going to be more like a curve. But we also don't want these islands. These islands are indication that it's overfitting, right? So how do we solve these complex problems? And the problems become even more complex. For example, here's a complex task, right? So we train a linear model to detect this horse, if the picture contains horse. And we provide lots of training data. And so it learns to detect a left-facing horse. But what about if the horse is right-facing horse, right? These models, if you train a linear model, they don't work well. Like they simply won't be able to detect these small differences in the data. How do we solve for that? That is where deep learning comes to rescue. Deep neural networks are extremely powerful, and the power comes from two things. So one is when it comes from nonlinear modeling, like I mentioned here, right? For like I showed here this, right? For complex data distribution, simply a line or a hyperplane, right, does not work, right? So we need like functions that allow to have curves, right, that separate the data or fit the data well. So it does have the nonlinear component, but in addition to that, simply nonlinear component, like in this problem, right, is not going to help as well, right? So what we need is to learn abstract features, right? So deep neural networks, they have these hidden layers. Right? So I'm going to walk you through this example, and hopefully that starts to make more sense. So in this example, we are giving the machine learning model this picture, and the model detects whether it's George Washington or other folks here, right? Maybe Jefferson and Clinton and so forth, right? So other presidents. So the way deep learning model will process this is so the first layer, it goes layers by layer, right? So the first layer is in this particular DNN network, it's identifying light, dark pixel values, right? The second layer, which is the hidden layer, and hidden, we call it hidden because we don't know how exactly what exactly it is, how it is modeling. These are abstract features, and so it is likely doing something like identifying edges, right? And people have found ways of visualizing it. That's why we can say that confidently. The third layer is identifying combination of edges, right? And then this fourth layer is identifying features. And finally, this fifth layer is able to predict which president we are looking at, right? In this input picture. And this is very powerful because this can solve left-facing George Washington, right-facing George Washington, right? Like pretty much any variation of those different color backgrounds and so on and so forth, right? Here's another example where this deep learning network can detect multiple objects in the same image, right? So here it's detecting a car, a person, and an animal in this picture. And that's a very complex problem, but it's able to break it down, right? It's able to learn these abstractions. And so the interesting thing here is a lot of the intuition behind this technology and research that has gone into in the last 20 years, it came from how our minds work. So I want to be very careful here, and I don't want to imply that this is exactly how our mind works, but like I said, in computer science, everything is a model of real world, right? So we derive intuition from how things work in real world, and then we engineer systems. All machine learning systems are engineered. They are magical, but there is no magic happening, right? They look magical, but there is no magic happening. Just to break it down here, each neuron here it looks like this, right? So it's getting the input. I wouldn't go into too much math, but it's still learning the weights, the same concept, right? Where we looked at the Celsius to Fahrenheit example, we were just learning the weights in that function, the parameters. So it is still doing that. Now it sums up across various attributes because the input may be just the array of pixels for this image, right? It sums it up. It is still linear to this point. Now, something very important happens after that. It is fed into a non-linear function. That's how it's able to learn those curves, right? Fit the curves, not just a line or a hyperplane, right? And that output is fed into the next layer, and so on and so forth, right? In terms of the learning, the same concept that was applied to linear regression, the actual and predicted value and reducing the loss. Same thing is applied here. And then it basically there's a technical back propagation. So when we train, we provide this value. Let's say first time when we are training, it may say that, oh, it's looking at a picture of Jefferson, but it is actually Washington, right? So then we correct all the values of the weights going backwards from here. That's what's called back propagation. And that requires lots of matrix multiplications and derivatives and so forth, right? And that's what requires computing power. So then we feed some more images of different residents, and we keep on doing that many, many times, right? And eventually this network gets trained, all the weights are assigned very well in these embedded these hidden layers. And then it's able to predict with much greater accuracy. And that's really how this works. And it's not that easy to design these complex networks. So there's a lot of tuning and all that happens here, but that's like fundamentally how deep learning works. And I want to just quickly talk about, so we talked about there's so much data that's needed to train these networks, right? There's also a lot of computing power that's needed. But how can every team do it, right? How can every small team that may not have those resources use deep learning? So the interesting advancement there that has happened is a concept called transfer learning. In traditional ML, we use a data set, we learn a system that solves a particular task. But this knowledge is very specific to this domain and cannot be transferred. Transfer learning, on the other hand, we can basically leverage what is learned and apply that to other tasks and domains, right? So that's where things get interesting. We have very large models, for example, GPT-3, Microsoft's natural language NLG model with the NVIDIA partnership. And then there is the Google Brain and so forth, right? So, and for example, Google BERT, the BERT model, we can take a pre-trained model and just add a couple more layers, right, to it, and just use our new data set to train those additional layers, and voila, we can use that model. So we are building on already learned knowledge in this pre-trained model and just tuning it to solve our problems. And that is the power of this transfer learning. So there's more and more frameworks, APIs, platforms that enable that. And hence we see the explosion of how deep learning is being applied in many different domains and many different tasks. There are many different types of neural networks, deep learning networks. So, I mean, each of these can basically, it's a very big field in itself. And I just wanted to show this slide to give you a sense of how deep learning is being applied in many different problem domains, right? So it's not just the simple example that I showed here of image detection. The supervised model training process, so high level, basically how we train the model, right? So we take the data, and of course before that we have identified what data, what features, meaning what factors, right, that determine the output or that influence the output, right? That's what we are taking data into consideration to train the model. Then we split the data into training, validation data, and test data. And as we apply this iterative learning algorithm, right, because it's a supervised algorithm, it will keep looking at these examples and refine itself. And once the model is built, we want to validate it on this validation data, right? And then tune the model. So we talk about tune, we're talking about hyperparameters. lot of these learning algorithms have many different parameters that we want to adjust, right? So that it can learn better. Once that is done, then we do a final test on this test data. It's very important to separate out these two, validation data and test data. We cannot get to prevent overfitting we talked about, right? Because it's if we disclose test data to this learning algorithm, it will just learn to do well on test data. And when we roll it out in production, in real life, it's not going to perform well, right? So it's very important to not introduce that bias. And also with these iterations, we don't want to do it too many times, right? If the model is not working, algorithm's not working, we go start fresh. Quick, this is like, how do we evaluate the model, right? How is it performing? So this is a very common metric here called precision recall. And I'm not going to go too much into it. There's a number of tutorials on this. I just wanted to keep it here. But basically, one important call out here is accuracy is not always a good measure in terms of how you evaluate a model. So for example, we are building a machine learning model that predicts a rare disease, right? And that disease occurs like 1 in 10,000. So we could build a model which predicts all the data points as like all the time it's predicting the disease is not found, right? Not positive. So that model would be basically 99.99% accurate, right? But it's useless because it's missing the one real data point that matters, right? Where the disease was actually present. So we have to be careful about how we use accuracy, especially for unbalanced data sets, like, where one class is very rare and the other class is the predominant, right? So for example, rare disease detection. So we want to look at precision recall and some of these other measures. This is another popular ROC curve, right? So there's a concept of threshold. So if the model is predicting something using a probability distribution, right? So probability that a picture is George Washington's picture, right? So if we set the threshold too high, it will predict George Washington only when it's highly confident, right? Obviously. But if you reduce the threshold, then you start to see some false positives. So some of the images, it might say George Washington, but they may not be, right? So that's how we set the threshold, and it's one of the parameters when we put model in production. How do we know the quality in general of the machine learning? So that's where this ROC curve comes in, where it's the true positive rate and false positive rate. This curve, we want it to look like this, right? Not inverted. And the area under this curve should be greater than 0.5, because that's when it indicates that the machines, the ML models power to predict true positives is greater than false positives, right? It's doing much better job in giving you true positives, meaning it's right more often than wrong. Yeah, I just wanted to keep this here, so you can look it up further online if some tutorials and other things, and use this as you work on your ML models. This is just a quick call out here that machine learning code itself, right? It's a very small portion of the overall solution that we engineer. Much of the effort goes into other things just related to data collection, verification, feature engineering, the most important thing, right? And obviously all of these operational things that we need to do to continue to model, maintain, run, serve the model as well as continue to retrain the model as there's data drift. So yeah, just generally people think about like, okay, machine learning, I got to do learn is all about basically machine learning algorithms and coding and all that. That is not enough, right? There's a lot of data engineering and all these other disciplines that need to come together to make the ML ops practical. All right, so I talked about feature engineering, which is, I think, here, right, it is one of the very important things. So I want to spend a little bit of time there. Features are the factors, like the input data variables we model to predict the output. Right? So for instance, for output is, let's say, the house price that we want to predict. The features would be square footage, the condition of the house, the school district it is in, longitude, latitude, or the city is it, and etc. All that, crime stats, whatever. Selecting and modeling the right features has the biggest impact on model performance. Like I mentioned, all the ML engineering systems are engineered. So it's not like we just throw a lot of data at it and it will figure out automatically what we are interested in. Although deep learning models, like just we looked at, right, they're pretty powerful in dealing with lots of data and trying to really learn these abstract features. But still, it just makes very hard for machine learning to learn with lots of raw data, right? And so good feature engineering can help it learn faster, use less data, and so forth. Quickly, if we just use fewer features, how many features we need, right? Fewer features would lead a simple model, will be easy to train, right? It will require less computation, but it will have high bias because it's not considering all the possible factors in predicting. But it would have low variance, meaning it will generalize well, right? Because it's not too specific to the training data. If you use lots of features, the model becomes very complex, right? It is highly dimensional, need lots of data, right? There could be noise and other things that you need to deal with, lots of computing, but it would have low bias, meaning it would be very considerate of all the factors that come into play, right, that influence the output. But it would also have high variance because, one of the things like we talked about, you don't want to overfit it. So yeah, there's always, you want to find the right balance of what features you're using. And there are many techniques to help you with that, right? Normalization and regularization and all that. So I just listed a few here that you should definitely look into while you model, build your model and select and do the feature engineering. What data can be used as features? Literally any data or a combination thereof, right? So structured data, that is like typically what you see in Excel, in database, right? Any like categorical, numerical, etc., whatever. It's in some sort of a structure, right? In columns. Text data, right? This is what we use here in FinOps a lot. We get millions of emails, and so we're trying to always apply machine learning to automate various things and derive insights. So this also you can model in any way. There's no right and wrong way to model it. It all depends what works for you, what output you are seeking, right? So you can use letters, what people have used, words, partial words, sequence of words, like phrases, sentences, parts of speech tagging, like combining that with NLP, right? Even bytes, right? People have just tried to use bytes and see how they perform. So ML by itself, the ML problem solving is very unstructured. It's not like a functional programming. You're given specs, just go write the code, get it done. You have to do a lot of iterations. You have to kind of figure out what works, double down on that, right, and try different things, or course correct sometimes. Images like vector of pixels, audio, again, processing, video, time series data, pretty much anything can be modeled and fed into a learning algorithm. So in summary, basically, this is my recommendation here. Anyone wanting to use AIML, please spend more time on just framing the problem, right? You understanding the business process. Look for opportunities that can be framed into this like a classification. I'm trying to classify, categorize, label, or just regression, predict house price, continuous, right, height or things and disease, all that. Look at live data examples. It's not just enough that, okay, I understood the business process, immediately jump into creating a model and then feed the data and then, oh, it's not working so well, or just keep working at it for months and months. Just using some live data examples and identifying all the factors that influence what you're trying to do, the output, that would help a lot. Specific, take a sample, study the data examples, find ways to try different techniques to get the right features out of that, right? Out of the data. And then first try classical machine learning models, logistic regression, the most common ML algorithm used, right? Works. There's other decision trees and then KNN and just simple models. Any model, if you try, at least it will help you. If you iterate on it, it will help you arrive at the right features you want to model. And then definitely leverage what's already out there, right? Azure Cognitive Services has a number of language models there, like sentiment analysis, all those things like key phrase extraction, sentence extraction, summarization. See if that works, right? Include that in as part of your solution. And I talked about transformer models, right? They're just super awesome. You can take that model, just enrich it with some of your data based on your domain, right? Add additional training layers, and it can do wonders. And explore deep learning. I think we don't need to be, it's a very vast, very advanced, complex field. Almost every week I see new research papers coming out and just amazing techniques, amazing developments. But there is still, over the last few years, there's been a lot of powerful platforms, frameworks, APIs, even like the studio, like no code, low code stuff, right? So it's not that scary. You don't need to learn a lot of math and all that. Just have this intuition, how it works, and go and try it. So with that, I'm gonna just give a quick glance on some of the state-of-the-art AI/ML. Hopefully we'll have some time for questions. So this one is called Google Imagen AI system. So this is text to image. So just to showcase type of cool things machine learning and especially deep neural networks can do, right? So here, like the input is we are providing an input like a golden retriever dog wearing a blue checkered beret and red dotted turtleneck, right? And this is the input, and the machine is actually generating the image based on that. And this is just incredibly cool. Should click on this link here and see the number of other images it can generate, and they're just, some of them are surreal, beautiful, but just absolutely amazing. So yeah, please check out this link. And this is like this, it's using a diffusion model to generate that image from text and encoder decoder networks. So pretty awesome, very cool stuff. Google also came up very recently. There were a number of new research and just projects that got published in the last 1 year. And this is another amazing one that created a lot of waves and also some controversy. So the Google Lambda AI is a conversational AI, and there's a long transcript of the conversation that one of the engineers and a collaborator did. The engineer's name is Lamont, and there's another collaborator with him. They posted this transcript online, very detailed, and should take a look at it. It's shockingly good. There's some snippet here that Lamont's talking about. So what is the meaning of broken mirror specifically? And the AI is responding, maybe to show the enlightenment is something you can't unlearn once you have acquired it, similar to how you can't repair a broken mirror. That is some cool response there. And it goes on and just like human-like conversation, really, right? I do want to caution that we don't want to get this. The controversy was around, like, people arguing if Google AI has is sentient, meaning, can it feel? And it's really like you should really go through the chat script here and see for yourself. But I mean, my take on that is basically, like I mentioned, right? All these systems are engineered and they're so powerful, they can riff through pretty much like the entire body of literature that's out there, right? And learn and come up with amazing things. I don't think the AI model itself can feel or has any consciousness in it, but that's my take on it. There's another project here, Google Minerva AI, where you pose a question and it gives you a solution. And this is a mathematical question. And these examples are like this. The left one here is from joint entrance examination, right? JEE is one of the toughest exams with like it's taken each year by 2 million Indian high school students. I was one of them when I was applying for engineering college, right? And this was something, and AI is solving that, right? Here's another example: national math exam in Poland, right? The 270K high school students every year, they take questions like this and solve for it. Read more here at this blog. Here's, thankfully though, well, I don't know, well, hopefully, well, this it's not perfect though. This this same Google Minerva AI model didn't do so well on some of these questions. So again, but the way these models are advancing, it's pretty amazing. Here's another one from Meta AI, Meta Facebook, and this is pretty amazing. Also, this is probably the first time they have speech-to-speech translation. Typically, the speech to from one language to another, it goes through like basically speech to text and then text to another language, pairwise, all that. Over the years, then we had these canonical language models that so on and so forth. But anyway, this is very powerful because it's just taking directly speech to speech with like no text generation involved in the middle. And this is amazing because it is for over 200 languages. Many of these languages are not even written languages, so it can translate those. That is amazing. And learn from those and translate. And then like talking about these big models I was talking about, right? So here's this Microsoft NVIDIA Megatron Turing NLG, right? That uses 530 billion parameters. So these are like the factors, the features I was talking about, right? I mean, the parameters are the weights for those. That's how gigantic it is. But once this is trained, right, this is across for all natural language. We can use the transformer model, right, to leverage this model and then solve for the problems in our domain. Finally, I want to call this out here. This was interesting, which I saw on my LinkedIn feed a little while ago. And this picture, meet the world's first artificially intelligent magazine cover, right? So this cover page was generated using AI. And on the foot here, you see it like under the foot and says, and it only took 20 seconds to make. So just implies that AI just generated this in 20 seconds and that was all, right? But the real truth is like highlighted here, right? It was not magically made, as Ali says here. She's a global head of AI at Amazon. It was not magically made. Karen X. Chang created the cover with the help of AI. Without Karen and the AI working together, this cover would likely not exist. Second, it didn't take 20 seconds to make. Karen's personal behind-the-scenes video mentions kickoff calls and creative reviews, hundreds of prompts, thousands of options, and hours of design, right? So here's an example just to highlight that, we don't need to be really fearful of AI, right? I see the future where we use AI just like we use all the tools to other tools, right? And software and systems to improve our productivity. It's the future I see is humans and AI working together. Of course, there's gonna be a lot of disruption as things get automated and things like that. But we've seen that before in Industrial Revolution and so many other things. And Change is the only constant. So, but humans are exceptional in our abilities to adapt, right, and grow and advance and push the boundaries. So, yeah, that is it for this session. Happy to take any questions.